So I'll start sharing my screen. Is my screen visible to you all? Okay then. So, so let me introduce myself. I'm a fifth year research scholar. I'm a Prime Minister Research Fellow and I work on developing composite cylinders at IIT Kharagpur. So this is a doubt-solving session of the NPTEL course named as Introduction to Composites. And I'll start with the first doubt. So, so it's here. Um, it was posted that if the fourth question of week assignment had the answer as D, that is all of these. So yes, you're right. The modulus of any composite depends on the properties of the fiber as well as matrix. So if you are trying to calculate the property of the entire composite, you will take the percentage of fiber, percentage of matrix, and the properties of fiber as well as matrix into the formula. So this is the formula which is used, and as all these three properties were there in that question, then definitely the answer would be 4. That is all of these. Does anyone have a doubt in this question further? Okay, if not, we'll switch to the next question. So in this, one of you asked that are cements fibrous or particulate composites? So it's actually quite nice question. I mean, you can learn a lot out of it as you don't actually categorize a composite as fibrous or particulate individually. Composites are mainly categorized into broad categories. One is on the basis of the reinforcement materials which are using, and the other one is on the basis of the continuity in the entire composite. I mean, one would be the materials which you are using for making that composite, and the other would be continuity. So, if you are using, suppose, glass fiber composites, or glass fiber made composites, or carbon fiber made composites, then those all are long fibers. Or in case of discontinuous composite, they are all like small pieces of fibers which are just dispersed into medium, which is something similar to a glue. So that is what constitutes of a composite. So if the particle size is very small, then it would be particulate composite. But if the particles are continuous, as if you have long threads dipped in glue and then you're just wrapping around something, then the composite made out of which would be entirely continuous composite. So that would be something which is opposite to particulate composite. Are you understanding my point? Like, particulate is the one in which there are particles dispersed into the glue medium, while the continuous ones are those in which long fibers are there, everything is dipped in the resin system and it's just rolled around something. So, due to this, uh, like if you want to categorize composite individually as particulate and continuous, then it will just depend on the size of the like two components which you are using together. But if you are considering the other one, that is on the basis of the materials which are used to manufacture those composite, then you can classify those composite as fibrous or metallic or polymeric. Like it will depend on the raw material which is used. So as a question, is cement a fibrous composite or particular composite? Then the answer would be that it's a particular composite, as most of the cements which are used are for like e- establishing more heat resistance for operation at higher temperatures. So in that, there's a uniform homogeneous metal matrix, and small particles of this carbide, oxides or sulfides are all dispersed in between. So they're all particles, therefore they are particulate composites. Okay, is it clear? Do you have any doubt further in this particular context? Oh man, interact a little, or else you'll learn nothing out of this doubt session. Anyways, so now I'm moving on to the next question. So the next question was, is it possible to have liquid composites? So uh, the composites with which I have dealt till yet were all solids. Well, the basic concept behind designing a composite is you have two different materials. Both have quite like um, different properties. One will have high strength while other will just like bind everything all together. It's something like that. Or one will have high strength while other will have quite good electrical resistance or heat resistance. So that's the reason we make composites. So it's actually possible to have liquid composite, like research is going on it, but typically in commercial use all the composites are solid because during manufacturing we may have liquid region which is there. Once we solidify it or harden it in order to obtain the desired property in a composite, most of the composite which exist around us are all solids. Okay. So I hope this question is also clear. Then these are some examples. For example, plywood is a composite. In this, wood is there which acts as the reinforcement, and we have for phenol formaldehyde or urea formaldehyde which acts as the glue system which binds all the wood layers together. So we can see this brown section is the wood part while the yellow section is the resin part or the glue part. So this glue would be placed between like one layer after the other to bind all the wood surfaces together. Then we also have granite. So in case of granite, we have many crushed pieces of quartz, stone, dust, and like other particles which are well homogeneously dispersed in acrylic resins. So again, in both of these cases, the raw materials used were one solid and other one liquid. But the final composite which was obtained after hardening and post processing was overall solid. So that's it. So do you have any other doubt relating to this question? No? Okay, then I'll move to the next question. This question is also quite interesting. In this, one of you have asked that in this video at this particular like time, uh, the professor explains that when the strain rate is higher, then if we have fibers, then they have higher modulus and strength. So let me first explain you what is strain, strength, modulus, and everything. So this is the typical stress and strain curve which we obtain on mechanical testing of any like solid substance. So we have this curve. This one would be the initial section, that is the Hookean region. Then this is a typical curve of a metallic body. But if we talk about fibers, then fibers only go from here up till here, then they yield at this particular point and they break here. So how do we calculate the yield strength? We take the initial strain, then 0.02% of this strain we draw parallel line up till here, and then we see the cross section. The cross section of this stress strain curve with this 0.02 strain line which is parallel to this particular line would give us the yield strength. So the strength about which Professor Nachiket is talking about is the strength which is intersection of this strain line with this stress strain curve. So it doesn't actually depend on the slope of this curve or any other region. It is just the strength at which the fiber will start yielding. Okay. And then the modulus would be the slope between the slope of this line. That is the stress at this, if we are trying to calculate modulus at this particular location. Then from here up till here, the change in stress and the change in strain would give us the modulus value. Okay, so these were just the basics about how to interpret a stress and strain curve. Like if you want to find the modulus of the system and the yield strength, then you'll have to do two things. First is to determine the slope of this straight line, which lies in the Hookean region of this graph. And the second would be find the intersection of a line which is parallel to this particular line, but the strain is 0.02 times of the strain at the initial location. As you all are mechanical engineers, you might already know this point. And so the point which Sir tries to explain here is that if you suddenly increase the strain rate, then in case of fibers, the overall modulus and the yield strength which would be obtained would be higher. So, like, is there anyone of you who has ever done used UTM machine for doing tensile test or compressive test, any kind of mechanical test? Is there anyone? Somebody answer. See, if it's going to be a one-way session, then I don't think you'll learn a lot out of
Yes,
it.
yes, ma'am. I have carried out.
Okay. So in that case, like this is the UTM machine which is there, like commonly used. So as it's seen here, we place the sample in between and then we like stretch this machine. Like this is the fixed surface. Well, there can be two kinds. One we can stretch downwards, one would be other one. So we apply tensile stresses at a particular strain, like load rate, and then we get the stress versus strain curves. So in this video, I just found a normal video from YouTube. In this, they are trying to test the tensile properties of a steel cylinder. So we can see they start increasing the load and they can see a change in the strain. So this graph is rising gradually, and the rate at which the load is applied, that is the like millimeters per minute of shift in this load cell, would be a test speed. So we can have different test speeds as per our UTM machine. It could be something between 0.5 up till 14 millimeters per minute too. And using this, we can have the tensile test results. So we can see we are increasing the load this way, and the load is increasing and the strain is also getting generated in the system. So this is almost a straight region. This is the Hookean region which I was talking about. So we can see here the like graph starts changing. So here is the point somewhere where yield strength will occur, and from here it starts deforming, and we can see it will break. Like see, after some time they'll show that it breaks. So the stress at which it breaks would be the break strength, while the stress at which yielding starts, that is when we see a change in that stress strain curve, would be our yield strength. And if we want to calculate it, then yield strength would just be when we take the same slope as this straight linear line and we shift the strain by 0.2%, and then the intersection with this curve would give us the yield strength. So the yield strength and modulus are determined using this method, and a higher strain rate typically means that we'll increase the test speed. For instance, in this experiment, the test speed would be around 2.5 mm or something similar. If we suddenly increase the test speed from 2.5 up till 14, then the strain rate would increase a lot. That is what Sir was talking about. That is, if in case 2, we have instantaneous loading. That is, in small amount of time, we can obtain like larger strain rates, which are required for the testing, which leads to break. Then fibers will give higher modulus and strength as compared to other materials. I understand, like even if we give an instantaneous impulse kind of load, still the fibers would not fail that early as compared to other materials. So that's why they are preferred for designing high performance composites. So as we can see, when we move from here up till here, this is the stress strain curve of a fiber. This is the matrix. And using the formula which I talked about here in this slide, that is the question number 4 of week 0 assignment. The longitudinal modulus can be calculated by using this formula. So we can see for in case of composite, the longitudinal modulus, that is the slope of this particular line, will lie something in between the slope of this matrix stress strain curve and the slope of this fibers curve. So uh, that's all I think. So do you have any other doubt, or else these were the doubts which were posted in the discussion forum?
Ma'am, would you please take assignment number 0?
Take, like, do you want me to discuss it?
Yes, ma'am. Yes, ma'am.
Okay. So there were 5 questions, I think, in that assignment. And the first question was identify the appropriate matrix material with low cost and high operating temperature. So, a a particular matrix material will have high operating temperature if its melting point and glass transition temperature. Every like has any one of you ever worked with polymers? Do you know what is glass transition temperature and melting temperature and how do they differ? Answer?
No,
O-
ma'am.
Okay. Then in that case, when we are
Yeah,
characterizing,
madam. I can tell.
okay then, come on,
Yeah,
Krishna. Then say
yeah, yeah. Glass transition temperature actually that hard substance to soft
yes,
soft substance it will transfer.
yeah.
And the melting point temperature at where actually it can be done the curing the polymerization when you start that you can do the melting and you can do. Okay, maybe
Yeah, the
I
last
understand.
point was you said the definition of glass transition temperature to be absolutely right. So polymers are normally viscoelastic. That is, when we are trying to thermally degrade them, then first they behave as solid materials. They uh, like they'll follow Hooke's law. They'll fall in the elastic region, and gradually, as we increase the temperature, they start to transition. They start having transition into liquid phase. Okay, that's the mechanism in which polymer starts degrading. They'll initially behave like solids, and then later they'll start transitioning into liquid state. So the transition point where the polymer starts behaving like a rubber like material, that is its elastic property has gone a little, then it would be that region is known as glass transition state, and the temperature at which it starts that transition is known as glass transition temperature. But the melting temperature is when the solidified polymer completely melts into liquid. That is, it will entirely melt. It will be entirely entering into the liquid state. So this is the difference between the two terminologies. So in this question, they are trying to find the polymer which will have higher operating temperature range. So the polymer, it's expected that the polymer will always like be operating in the elastic state only. The major function of that polymer would only be met if it's able to provide the mechanical properties which is required. So when we go into literature and try to find out the melting temperatures and the operating temperatures of each of these polymers, we can see the results are as follows. Like this, you'll find on web too. It's nothing new. But then, if you try to study it conceptually, then the melting temperature normally depends on the cross-linking which is present in the polymer. The higher would be the cross-linking, more amount of temperature it will require to get a transition from its solid state to liquid case. Why is that? Because when this polymer is getting liquefied, then the covalent bonds and all the cross-linking interactions which are present between two parallel or like polymeric chains, they all break apart. So, if we go chain wise, like from chemistry point of view, then this phenyl chain is quite haphazard, like it's in a zigzag pattern, and that too large zigzags. So, the cross linking between this would be more complex. That's why it will take a lot of time to melt. Then this one is a straight chain. We have a benzene ring and we have a sulfur ring. So this is all straight. It will melt quite like easily compared to this one. When we move towards this nylon 66, it's all straight chain with only carbon units in between. So this is the easiest to melt out of these four. But when we go for Teflon, this is as such it's a straight chain, but it has comparatively higher temperature because we have these fluorine atoms. So these fluorine atoms have high hydrogen bonding. If somebody might be there in chemistry from you all, they might know that fluorine have high tendency to form hydrogen bonds, and that's the reason this Teflon also has higher melting points compared to like the other two. So from like this observations we can see that teak as well as Teflon both have almost similar melting temperature and operating range. However, this one is the most low cost and high operating temperature polymer matrix because its chain is most suitable for like operation. Okay, is it clear? Okay,
Yes, ma'am.
anyways, so I'll move to the next question. So in this they've asked which one of the following will have highest strength. So again strength also depends on cross-linking. When we compare all of these together, the ones which will have straighter chains will have highest cross-linking which is very uniform. So when it comes to strength, crystallinity also play an important role. So that's why when we are talking about epoxy resin, it has many oxygen groups, so there would be hydrogen bonding. The chain is also comparatively straight, so cross-linking would be more like well arranged, and that's the reason epoxy has higher strength. When we choose commercial composites, then the composites which were made using epoxy as the glue region have very high performance as compared to the other ones. While epoxy is comparatively costly, and the other type of resin which is normally used is polyester and phenolic. So phenolic have very high operating temperatures. That is the composite which are used for manufacturing, like the composite which would be used in spacecrafts for the external surfaces of aircrafts or the bodies which tend to be operating in higher temperatures are made out of phenolic resins as they don't melt even at 1200 degrees Celsius. Like there can be exceptions, but most of the grades of phenolic resin doesn't melt even at 1500, 1600 degrees Celsius. In case of epoxy, we have high strength, but its cost is a little higher. In case of polyesters, we have normal strength, but the cost of this polyester resin is quite low. So for general applications in vehicles and like the molds which we use in cars, which are all made of composites, these polyester resins are used. And polyamide is it's simple nylon, so nylon is quite famous as a polymer. It can be used in many applications. Then the other assignment was which of the following is the terminology used for single layer fibrous composites. So it's quite simple. Lamina is the term which is used. When lot of laminas are placed over one another, then this entire stack is known as laminate. Then this I have already discussed in this doubt salvage session earlier, as the longitudinal modulus of the lamina depends on all these three properties. So that's why 4 is the right answer. Then this is an interesting question if you want to learn the basics about composites. So in this question they have asked that experimentally the volume fraction of void is determined by. So First, let's talk about what's volume fraction. So this is the cross section of a composite. Composite from the top surface, it looks something like this. So we have fibers in these orientations and resin is poured over it. So once the resin entirely solidifies, the entire composite is ready for whatever purpose it wants to serve. So if we want to, then there are air voids present between these fibers and the resin system which we have poured into it. So that volume fraction is what is asked in this question. So this is the top view. If we try to view this composite from side, then this would be the cross section. These all small circles are the fibers which are present. Then this black part is the matrix material, that is the glue which is uniformly dispersed over here. Macroscopically it's uniformly dispersed, but when we go on to micro scale, this scale as it's seen here, it's 10 micrometer. If it's so small, then we can see that it's not completely homogeneous. We can see here the resin content is more, while here the fiber content is more. But when we move towards millimeter level, or the levels which we can see with our naked eyes, then in that case the composite is considered to be macroscopically homogeneous. So we can see here this cross section illustrates the volume of fiber and the volume of resin which is present in this particular composite. So how will you calculate the volume? Either you take the entire cuboid and assume that there are many cylinders of this particular diameter and the length which is equivalent to that cube, and there is resin dispersed in the entire volume. This is how you can have the volume. Or if you are considering a very small part of this composite laterally, then you can just calculate the area which is there. So area would be this pi r square, which is diameter of each and every fiber. This is all homogeneous. For example, in case of carbon fibers, the diameter is around 7 mu meter. So if we want to calculate the cross sectional area of one carbon fiber, it would be pi into d square by 4. So diameter is 7 mu meter. So using that, we'll have the cross sectional area of each and every carbon fiber. Now we'll count in this image that how many carbon fibers are present. Then we'll also try to have we'll also have the area of this entire section. Then this entire section area minus the area of these fibers, which that will give us the area of the matrix which is there, that is the left portion. So using that, we can estimate that what would be volume fraction of fiber and the matrix individually, if you are not considering any air voids in between. But if you like further magnify this image, then you will see that the interfacial bonding between this fiber and the resin system, we can see there are a lot of air voids present, this white colored dots which are small. So these are known as air voids. So in this figure, it's even more clearly visible. This huge voids are the air voids which develop in the system while we are manufacturing this composite. So these leads to effect. If we want to calculate the percentage of air voids which are there, what we do is we measure the volume of the initial system. Then we burn that sample. When we are burning it, the resin is a polymeric substance. It will melt, and after some time it will start completely evaporating into gaseous phase. While the fibers are all glass fibers or carbon fibers, they don't degrade even up till 400 degrees Celsius in case of carbon fiber and 600 degrees Celsius in case of glass fibers. Metals are even better. Metals don't even degrade up till 700 degrees Celsius or even higher. So in that case, we'll evaporate all the resin which is there in this sample at lower temperatures. We'll only have the fiber which is there in the burnt out sample along with some impurities. So we collect that burnt out sample and we wash it with acid. So that acid part will remove all the impurities. Fibers are still non-reactive, so it will have no reaction with acids, and therefore we'll have only the percentage or the mass of fiber which is there. So we'll calculate mass of this entire system at three phases. One would be the mass of the washed out fiber which is entirely clean. The second would be mass of the burnt out sample which contains fiber as well as the burnt out impurities which were there in the composite. And the third would be the overall composite which contained resin, impurities, as well as fiber. So when we compare all these three masses together, then using simple mathematics, we can simply estimate what would be the percentage of voids in this composite. So that's why the answer to this question would be first. That is burn or acid digestion test. This is commonly known as loss on ignition test when we are dealing with composites. It's quite famous as a process, and you'll learn about it in your fifth year BTech or masters maybe. Okay then. So any other doubt? Feel free to ask. Any of you, do you have some doubt? Okay, if it's not, then we can end this meeting. Somebody at least respond.
Ma'am,
Yeah,
ma'am, in determination of theoretical stress concentration factor,
yeah.
we use epoxy resin model of our specimen. Why this is correct? Because metal has different properties and epoxy resin has different properties.
Where are you? Are you asking about this formula? This formula?
No, ma'am, no, different thing. Theoretical stress concentration factor, ma'am.
Um, is there some theoretical stress concentration factor? Just a second. Is there some another terminology for theoretical stress concentration? Actually, I'm from chemical engineering, so I don't have a lot of like my terminology is a little different from mechanical engineers. Does anyone know what is theoretical stress concentration? We have come across this point, but I'm not actually getting your question.
Actually, we make a epoxy resin model, and on stress bench we stress this,
Okay,
and some of photoelastic bench. The experiment is conducted on photoelastic bench,
okay,
and light is passed through that model,
okay,
and then uh, depending on number of fringes, we can conclude how much stresses are raised near the vicinities and irregularities in cross section. So my
okay.
question is that is it correct to use a epoxy resin model instead of metal?
If you're trying to determine the properties of epoxy, then you'll use epoxy. If you're trying to determine metal, you'll use metal. However, the problem is with metal is that the normal universal testing machine, that is the stress bench which you're talking about, they have limits to their stress load. That is the maximum load which they can apply for causing failure. For example, the machine which is there in my lab, it is around 30 kilonewton. So if you are trying to break a metal using a 30 kilonewton machine, and if its thickness is around 5 mm or something similar, it's actually impossible. In fact, even if you go up till 25 kilonewtons, you'll hardly get any changes in the stress of that particular metal. And that's why we use epoxy resins, because in case of epoxy, uh, the overall modulus of the system is very low. That is, you'll give smaller forces and you'll get comparatively larger strains, as seen in this graph, like it's here. This matrix, its graph lies so low. That is, you'll only have to give a like stress, which is force of around 1000 Newton, or like it depends on the thickness too. But yes, it's quite low. It's around 5 kilonewton or something, and you'll directly see the matrix like epoxy material breaking at this much of strain. But the same if you try for fibers whose modulus is something lower than the five, like metals have comparatively lower modulus than fibers. However, their modulus are like comparatively higher as compared to matrix. If you try to break metals in our in your stress bench, then this much amount of force, like force per unit area, would be required to break this metal. And that's why I think in your While doing experiment, they used epoxy resin instead of metal. The only reason was non-availability of that large capacity of load cell, or else it's not at all viable to have stress or stress strain data of particular material and use it into model of some other material. Are you getting my point? Is it clear?
Yes, ma'am. Yes, yes, clear.
Okay then. Any other question?
No, thank you.
Okay, fine. Then I'll end this meeting.